All right, welcome to some new slides. These are on trees, and a lot of this is stuff that you know from CSCI 41. So we studied trees hard there. Graphs, you can imagine, are a little bit harder than trees. So like, why did we study those before these? I have a good reason, and we will get there. All right. But yeah, let's talk about trees in general because they're a little bit different. The mathematical kind of trees. We learned about a very specific kind of trees in CSCI 41. We learned about binary trees. Okay, we learned about binary trees, and those are trees that are very nice looking for us. They had just 2 nodes coming out, right? Trees that had at most 2 nodes. Could have less, right? Those are binary trees. But in general, a tree is a special kind of graph. So that's why we study graphs first. So a tree is an undirected graph that is connected and has no cycles. All right? Has no cycles. So that's why we learn graphs first. And sometimes sometimes trees, we say that they have roots. And like for binary trees, we always said they had roots. But for normal mathematical trees, that's not required. Like you can say, all right, here's a tree, and like point at the root. That's fine. That's not a rooted tree. But you can also just have a tree sitting around, and that's just called a free tree, right? So that's how that works. So it's not required. So you can have just trees without any roots. That's totally fine. So it's easy to understand what leaves mean of trees with roots, right? It's just everything. Because you start at the root and just things kind of fall and they look like leaves now. But we define things because you're not sure which one's the root. There is no root in a free tree. So we say that a leaf in a free tree is just any node that's connected to just one other node. So like this is a leaf of the free tree. This is a leaf. These are leaves. Those are leaves of the free tree. Okay. Whereas like potentially, like if we said this was the root, if we made it a rooted tree, now it's no longer a leaf, right? So that's what we say there. But yeah, you can have leaves even if you don't have roots. And yeah, this is the generic kind of tree. And honestly, there's no like requirement about number of children. This can have 3 children. This can have 2 children. You have 1,000,000 children. Not a big deal. So here are some fun memes. And let us continue. So yeah, let's talk about trees with roots because those are the ones we care most about in this class and just in computer science in general. There's usually a starting point for us a lot of the time when we have trees. So let's talk about levels. So the level of a vertex is its distance from the root. So if this is the root, let's say that this is the root B, then this is level 0. All right, and then we'll call this one level 1, right? Because it's a distance. It's like a shortest path distance again, right? The distance from the root is like it's one edge away. Yeah, that's the idea. So this is level 2. See that? And so that's the idea. I think you can imagine like that's level 2, level 3, level 4. I don't have to write it out. The height of the tree, you could talk about the height of the tree itself. It's just like the max level. What's the maximum level you could have? It's the highest level of any vertex. 0, 1, 2, 3, 4. So for our tree, the height is 4. Thanks to that K node there. So height equals 4, excuse me. Can't talk and write at the same time. The idea of a parent is exactly the same as for CSCI 41, even though there's not just 2 children anymore. It's not a binary tree anymore. Just a generic kind of tree. The parent is the node above you, towards the root, in the direction of the root. And then we say that the root node has no parent. All right. So like the parent of F is E. The parent of A is B. B is the root though, so it has no parent. All right. And likewise, the parent is the thing above it is the parent. So the thing below it is your child. So like the child of E is F. D has 3 children, H, I, and J. Okay? And then if you want, you can use this is like a family tree at this point. You can talk about ancestors now. It's like, all right, G has a bunch of ancestors. It has H as an ancestor. This is parent. D is like its grandparent, so it's an ancestor. B is its great-grandparent, so it's also an ancestor. See that? That's like the idea. And so the opposite of that is the descendant. So like everybody is a descendant of B. The descendants of D are all these guys. I think you can imagine. Okay. I has no descendants. H has 3 descendants. Just the opposite perspective of ancestor. Leaves, the things that have no children, are defined like that. Leaves in a rooted graph or rooted tree have no children. So this is a leaf. All these guys are leaves. Okay. Those are leaves. And then finally, we have subtrees. A subtree, it's a smaller tree within the tree. You just pick a new root, and it's the tree consisting of that root and all of the original descendants. Okay? So let's pick out a subtree. So the only thing you have to do if you want a subtree of this existing tree is you say, all right, I want the root to be, you just say something. Let's say that we want the root to be D, and so from then on, we take all of its descendants. This becomes a subtree rooted at D, a subtree. You gotta take everybody. You can't be like, this is a subtree of B and just this. You can't like skip out on the D, right? That's the idea. You can't just like, I want this subtree with no G of H. That won't work. And then finally, there is a unique path from every node to every other node in a tree, which is very interesting, and we'll prove that. It's very cool. Actually, I can't remember if we've proved that or not, but it's a very good thing to know. There's only one way to move around, right? There's not like 2 ways to get from A to C, for example. There's not like from the root, like to get, you can go this way or you can go that way. There's no 2 options. There's just one way. Just one way. See that? So that's pretty nice. That's kind of what it means to be a tree. So here are some questions for you to try. So try to fill all these in, pause the video, give them a try, and then I'll show you my answers. All right, let's get some practice with these terms. So, all right, which vertices are ancestors of N, the node N? So ancestors of N. Well, just like, well, you got your parent, that's your ancestor, and then also your grandparent, so H and A. Let me draw that. I'll go back to blue for that. H and A. And then flip side of that, ancestors versus descendants. What are the descendants of vertex I? It looks like just E and F. It's 2 children. You would go further if there were more children of E and children of F. All right, what about the leaves of the tree? We have, I see C, E, F, D, and B. All right, so B is a leaf, even though it's really close to the top of the tree. It just has no children. That's what it means to be a leaf. So C, E, F, D, and B. What is the level of vertex D? So like, remember this is level 0. 1, 2, there's D, that's 3. That's level 3. Okay, so that would be 3. And then what's the height of the tree itself? Remember the height means the maximum level. Well, if this was level 3, one more is level 4. So E and F are like the lowest things in the tree, and they're at level 4. So the height of the tree is 4. Got it. At most, you take 4 edges to get to the bottom. That's kind of what that means. What are the level 3 vertices? Well, you kind of discovered that already. That's I and D. Yeah. So I and D. Draw the subtree rooted at vertex H. Well, that would be. Let me circle it for you since I don't want to. You can draw. I got things to do. So just the subtree rooted at H is just like take H and all of its descendants. That is your new tree. Okay. So there we go. So that's that one. Subtree rooted at H. And then we'll talk about, all right, what are the siblings? That's a thing, right? You can imagine that siblings are a thing. What are the siblings of a vertex I? Like, think of parent and child relationships. So here's I. What are the siblings of vertex I? Well, or is it like brother or sister? So like, siblings share a parent, right? So here's I's parent. What are the things that also share I's parent of N? It's just D. So that's the sibling of I. See, it's just like a family tree. Not too horrible, I hope. So yeah, those are those. Yeah, let me prove this one to you. I think we are going to prove it. Sweet. There's a unique path from every node to every other node. Theorem. Hee hee. There is a unique path between every pair of vertices in a tree. And the reason that this is going to work, remember the definition of tree. Dun, dun, dun. It's an undirected graph that is connected and has no cycle. This proof, it's going to be a proof by contradiction, what I was trying to show you up here, like, it's got to be, oops, where do I want to show that to? Undirected and has no cycle. There's only one way to get from one thing to the other. There's a unique path. I think I showed it here. Because, like, imagine there were two ways to get to F, for example. Like, you could have gone this way or this way. See that? Do you see how that introduces a cycle? That's going to be our proof. Okay? And a tree is not supposed to have any. A tree is connected and has no cycles. So, all right, here's our contradiction. There's a unique path between every pair of vertices in a tree. We're going to prove this by contradiction. So we're going to assume that our theorem is false. Assume that there isn't a unique path. Assume that there's at least two ways to get to a certain pair of vertices. Right? Assume. Because that would contradict the idea of there being a unique path. Right? So the inverse of this, the false idea, would be, all right, the negation of this is, all right, if there's not a unique path, assume that there's at least two ways to get to move around between two nodes. Assume there are two paths. There could be more, just at least there's two. If we're assuming this is false, it's not unique anymore. Assume there are two paths. Let's name things. Assume there are two paths. Call them path P and path Q between two vertices. Between vertices U and V, let's say. All right? So let's draw what's going to happen. So the idea for there to be two different paths between U and V over here is that there better be, like, if these are two separate paths, they're not the same, they must take different routes. Like, one way takes that way, one way takes this way, yeah? But the idea is, because they meet at U and V, like, maybe they both veer off. Boop. Maybe that's path P, maybe this is path Q. Maybe they veer off from the start and they share nothing. But do you see how if they worked like this, you can go this way, then this way, you've made a cycle? That's not okay. And so eventually, right, they have to meet up, even if it's like they meet up at U and V. But like maybe path P looks like this. There's somewhere, right? There's somewhere where they share a little bit. There's a place where they differ, and then there's a place where they share, all right? So let's talk about that. A place where they veer off. Okay, so let's say that this is path Q, and then this was path P. Do you see how, wherever this is, it could be U and V itself, wherever they start veering off, they do eventually have to get back on track because they both at least end at V, right? That's the idea. So somewhere this kind of picture happens. It could be at U and V itself. Doesn't matter, but somewhere in the middle maybe, or outside, they're going to diverge and then come back together somehow. Right? You see that? That has to happen because they both get from U to V. All right? And so imagine you followed these these differing pieces of this path. You went this way, and then you went back around this way. That creates a cycle. Hoo-hoo. So that's a cycle. And that implies that there was a cycle, right? If you could do this, that implies that there is a cycle in the tree itself. And a tree cannot have a cycle. Dun dun dun. So that's a contradiction. Contradiction. Yay. QED. So that means, that proves that there is a unique path. That you couldn't have had two separate ones. There's only one way to move around between nodes in a tree. There's only one way to get from, like, you pick two nodes, like E and K, there's only one way to get there. You gotta go through B and then down that way. Isn't that cool? So that's pretty cool. So that was the no cycles bit. I think we also have a proof that we'll use that deals with connectivity, but we'll get there. So, okay. Let's talk about this. So I'm going to prove to you eventually this theorem. This is a cool theorem. So let T be a tree with n vertices and m edges. If you are a tree, this is true for you. The number of edges is bounded. The number of edges must exactly be the number of nodes minus 1. It's pretty cool. That's the theorem I'm about to prove for you. But to get there, we need this lemma, this little helper theorem. So here is my lemma to prepare us for that one. Any tree with at least 2 vertices has at least 2 leaves. All right, and we're talking about free trees right now, by the way. Free trees. All right. Because I know, like, if this was a rooted tree, like, this would be only one leaf if you had just 2 vertices. But if you're a free tree, right? Free. There is no root, and so, like, anything with just one connected to one other thing, they would both be leaves. Okay? So that's what I'm trying to say there. So let me prove that to you, all right? So here is the idea. So what we're going to do is we're going to find so let's say we're going to talk about a tree, and we're going to prove that if there's at least 2 vertices, it has at least 2 leaves. What we're going to do is we're going to find the longest path, call it P in that tree, all right? So here's our weird looking tree. I don't know what it is. There's a bunch of stuff. Our tree looks weird. There's a bunch of stuff going on, but let's say that we have U and V on that path. Let's assume that we can find the longest path in the tree. That's always possible, and let U and V be the first and last things on that path. All right. So who knows what that path P looks like through this tree? But it looks something like this. Let's say there's my path P, and it's a tree, right? So it's connected to other things. Like U and V are connected to other things. Like it veers off. So this is what our tree looks like somehow. It looks weird, but let's say that this path P, the green one, is the longest one, all right? So we're going to show, by contradiction, that like regardless of the size of this tree, at least there were 2 separate nodes, right? 2 or more. We're going to show by contradiction that U and V must both be leaves if this was the longest path in the tree, all right? So here's the way. Let me make some room for myself. Let's move these over. Go that way. Oh, not like that. Go that way. There. So, okay, we're going to show by contradiction that U and V must both be leaves. So, all right, if we're going to do this by contradiction, assume that U and V aren't leaves. I'll show you that the world ends. Assume U and V are not leaves. Okay? Assume they're not leaves, and I'll show you a problem, all right? So if they're not leaves then, all right, what does that mean? That means that, all right, U and V are internal nodes, and, like, they lead to leaves, right? So, like, maybe there's a leaf this way. See that? There's a leaf that way. Or in some other direction, right? If U and V are not leaves, you could have gone further, right? You could have gone further out. Do you see that? Because, like, maybe the leaf is over here. Like, here's the leaf. Do you see, though, that if that were true, P could have been longer? This is not the longest path. Do you see that? But then we have a longer path because you could just go through those. Go through those that led you to a leaf, right? Because leaves are already not connected but to anything else. There's nothing you could have made that path longer. See that? You could have made that path longer by following it to those leaves. So U and V must have been leaves. But then we'd have a contradiction. Then we'd have a longest path. Because if U and V weren't leaves, you could have followed them to their leaves and made the path the longest path. The thing you were saying was the longest. You could have made it longer. Then we'd have I can't talk and write. We'd have a longest path. Yay. So that's a contradiction. Which means that U and V must have both been leaves. Therefore, U and V must have both been leaves. And that means that any tree with at least 2 vertices has at least 2 leaves. Which is a weird thing that you need to prove, but I promise it's useful. Therefore, U and V are leaves. QED. So there's our 2 leaves. We just discovered that they must exist. All right? So now, fun theorem time. So I'm going to prove to you that the number of edges in a tree must be exactly the number of nodes minus 1. And the way we're going to do it is by induction. We're going to do it by induction on n, the number of vertices in the tree, the number of nodes in the tree. All right? And so, base case, I guess technically you'd have a base case of the empty tree. No, you couldn't, because then m would be negative. That wouldn't make sense. So let's just do base case. Base case n equals 1. All right, let me prove to you that this is a thing. First of all, like here's just an arbitrary tree looking like this. That's a tree, right? Any tree you draw. How many nodes are in this one? 1, 2, 3, 4, 5, 6. 6 nodes. So n is 6. How many edges? 1, 2, 3, 4, 5. It's always -1. It really is -1, always. So that's not a proof. Let me prove this to you. So we're going to do it by induction on the number of nodes in this tree. So base case, what's the smallest number of nodes you can have in a tree that's like still there? 1 node. So what do I need to show for my base case? I need to show that m is equal to n minus 1. And n is 1, so that becomes 0. So m is equal to 0 in this case. I need to show that. Well, here's the only kind of tree I can make with 1 node, right? It can't be connected to anything. It's just there. There are no edges. So it does check out. So QED for my base case. Check. And then I need my inductive step. So assume it works for k, prove it for k plus 1. Inductive step. So assume, or n is equal to, in my inductive step, let's say that n is equal to k plus 1, all right? And I need to show that m is equal to n minus 1, but n is equal to k plus 1. N minus 1, which is equal to k plus 1 minus 1, which is equal to k, all right? And so I need to show that, all right, that is I got my dots in the wrong spot. That is a tree with k nodes, or with k plus 1, sorry, with k plus 1 vertices. Has k edges. So that's what I need to show right now. But I get to use, right, this is k plus 1. I can use the k, right? It's always p of k implies p of k plus 1. It's a direct proof. I can assume this. I can assume that it's true for the smaller one, for the one smaller one. I can assume that this holds when the graph is having only k nodes. That's my inductive hypothesis, my IH, that I can use to profit from. I get to assume that this works for k. I just need to show that it works for k plus 1 if I assume that it works for k. So, all right, a tree with k edges, k nodes has k minus 1 edges. Okay? And here's how we're going to use this to prove this, right? So we have a tree. And there are k plus 1 nodes in it. That's what we're assuming, right? Or, yeah, that's what we have right now to work with. Okay, so here's my tree. It looks weird. I don't know what it looks like, but it looks like this. What we're going to do is we're going to find a leaf of this tree, whatever it looks like. It could look like anything, right? All we know is it has k plus 1 nodes in it. So who knows? But let's say, like this is my tree. It looks weird. Who knows? Who knows what's there? What we're going to do to this tree of size k plus 1 nodes, we're going to find a leaf. So find a leaf, pick any of them, find a leaf, and consider the subtree without that leaf. Or, sorry, it's not a subtree at that point. It's just like it's a new tree. And consider the tree without that leaf. Without the node itself, so without the node itself, and also the edge that got you there, / edge. All right. So here is, let's say that this is a leaf right here in my tree of size k plus 1. All right. I know it's bigger than 1 for sure because we're not the base case right now. So here's my k plus 1th node, and here's the edge because it's a leaf. It looks like that. Okay. Let's consider the tree without this edge, without this node. Get rid of that node and the edge connecting it. So here's a different tree like this. So that tree, right? That tree without that node, how many nodes does that one have? That tree has exactly k nodes, doesn't it? Hoo-hoo, now I can use my inductive hypothesis. I get to assume that any tree with k nodes has k minus 1 edges. So therefore, that smaller tree, the smaller tree, has exactly k minus 1 edges by my inductive hypothesis. I get to assume that. Cool, cool. All right, what does that tell us about the original tree? The original tree with k plus 1 nodes. Isn't that nice? So I was able to find a leaf by this theorem, right? That's what I need the theorem for. Like, I was able to find a leaf. It had a leaf. It had a leaf I could talk about. And I was able to get rid of it and keep something there. So that's why we kind of needed this one, okay? So that was that one. And then now we're here. And all right, we got rid of that and we made another tree. We were able to find a leaf and get rid of it. We only need one, really. So therefore, if you were to add back in this node and this edge, what would that do? Because you knew that that smaller tree of size k had k minus 1 edges. You added in the node again, it's k plus 1 again. And if it had k minus 1 edges, the rest of it, you added one more, so that's k. That's what we needed to see. So therefore, the original tree was off by one edge, right? And one node. The original tree has k edges. I can't draw a tree in a way that I like right now. Tree has k edges. Bam, that's what I need to show for my inductive step. And so that proves the inductive step, QED. Beautiful, is it not? So that is our theorem. For any n, for any size tree, no matter what, 606, the number of edges is bounded. It's completely controlled by the number of nodes. To be a tree, the edges must be one less than the number of nodes. That's the only way it's going to work. If you have too few, then it's not connected. If you have too many more, if you have any more, then you have loops. You don't have any unique paths at that point. So it's got to be exactly that many, which is pretty cool. All right. Here is, use this proof, right? Think about this proof. I have a question for you that involves kind of this proof. I'm going to have you do it in a different way. Same idea, though. So here's a question. So I'd like you to prove that a forest with C components and N vertices has exactly N minus C edges. All right? So first of all, a forest, it's a cute little term. A forest is a graph with no cycles that isn't quite connected. It doesn't have to be connected. So a forest is just a bunch of trees. Isn't that cute? So here's a tree, here's a tree, here's a tree. And so it's got a bunch of different connected things. And I'd like you to prove by induction, again, induction on n, the number of vertices in this forest total, if it has C components, so this one has 3 separate components, right? And I claim that it has n minus C edges. Isn't that nice? So assume that n is bigger than or equal to C. So otherwise it doesn't make sense for that to be, can't have more nodes than there are components, because each component must have at least one node, right? So hint induction on n, and the base case is when n is equal to C, the number of components. Okay? Because you're assuming that n is greater than or equal to C. So the base case is like the smallest number of nodes you could have is exactly C nodes. Okay? That many components nodes. So give this a try. It's going to look very, very similar to this this theorem, and you might end up needing this lemma again, because you're gonna find this again. You're gonna draw that picture, and this is gonna be there again. Oh gosh, what happened? There we go. You're essentially gonna draw this picture down here again. I did it again. There we go. Hopefully you can see that. That idea is gonna work again. So give that a try. See if you can prove by induction on n with that particular base case the problem. All right. Okay. So here's the answer. So base case, we got n is equal to C. What does that mean? What I need to show, right? Need to show in this case is that the number of edges is equal to n minus C, right? But if n is equal to C, then that's just n minus n, which is equal to 0. I need to show that there's no edges at all. Can't have any edges. And okay, if there are just as many nodes as there are components, do you see how, like, all right, if there's 5 components and 5 nodes, there can be no edges, because otherwise you add an edge, you've made one less component. See that? So there can't be any edges at all, regardless of the number of components. Can't have any edges. Which is exactly what we needed to show. That checks out, so QED for the base case. And then our inductive step is n is more than that. N is bigger than c. So n is bigger than c, and then also like just say n is equal to k plus 1. All right. So what I need to show is that the number of edges is equal to n minus c again, which is, well, if this is n, k plus 1, number of edges is equal to k plus 1 minus c. Okay? I can use my inductive hypothesis, though. It's always use p of k to prove p of k plus 1. So I'm working with this, but I can assume, right, that the theorem is true for n equals k. If n is k, I get to assume by the inductive hypothesis then the number of edges equals k minus c. That will check out, okay? We've kind of fixed the number of components, so okay. That's the idea. And then, all right, do you see how in this step you can whittle it down? You can get a number, you can get this back down to k from k plus 1 by playing the same game and chopping off a node. So let me show that to you. So, all right, if n is greater than c, that means there must be at least one component, right? If n is equal to c, none of them have edges. But if n is greater than c, that means that at least one component of this graph, example graph maybe, of your graph in general, there must exist a component with at least one edge of size greater than 1, which means, according to our lemma, there's 2 leaves. I just need one. That gives me that there is a leaf, all right? So pick a leaf out of that component, all right? Pick a leaf out of that component and like cross it off. Out of that component, that's an F. And consider that smaller forest without it. I don't know if it's technically possible to call it a subforest, but it's a smaller forest at that time. So like, let's say that here's a component with at least 2 nodes in it. So let's chop off a leaf. So like, here's a leaf. Chop it off and the edge that got you there. Do you see how this smaller forest has 1 less node? And so now I get to use my inductive hypothesis about that smaller forest, because like if it originally had k plus 1 nodes, I've just whittled it down to a forest of k nodes. And I know exactly how many edges are in that one. I get to assume this, all right? So the subforest, so that forest, that smaller forest, has k nodes. Therefore, the inductive hypothesis applies. So by the IH, I don't like my writing right now. Let me do this slightly better. So by the IH, it has k minus c edges. Right? And then if you play the same game and you add in that other node and that other edge, that brings it on up to 1 more. See that? Adding back in that leaf gives you that k plus 1 number of nodes again, and it gives you 1 more edge. Do you see that? Adding back the leaf adds 1 more edge and node. So, therefore, the number of edges now in our size n plus 1 graph is equal to, well, it was k minus c for the smaller one, and we added 1 more back in, right, plus 1, and I need to show that this was equal to this, and it's like, the plus 1 is in a different spot. It is the same, yeah? So therefore that's true QED. Did you see that one? So it was kind of weird that you have to pick out just pick an arbitrary component with at least 2 edges. That was the hard part, but after that it really was the same kind of proof. See that? That's pretty cool. All right, a couple more tricks up my sleeve. Here's one more proof that I think you could do right now. Let's let G be an undirected graph with n vertices and m edges. You know exactly how many there should be if it were a tree, right? it would be exactly m minus 1, m equals n minus 1 if it were a tree. So if it's less than that, if m, this is just a graph right now, if the number of edges is less than n minus 1, that's like it would have been that if it was a tree, then show that it's not connected. Then G must not be connected, right? So try proving that. If m is less than n minus 1, where m is the number of edges and n is the number of nodes, G must not be connected, all right? So try to use the fact, there's my first hint, that trees have exactly n minus 1 edges, all right? And then my other hint is use proof by contradiction, right? So all right, if this is true about it, then assume it is connected and derive a contradiction. All right, so let's try some options. Let me show this to you. So for example, if this is a tree, right? This is m equals 2 edges, n equals 3. If I chop off an edge, see now it's smaller than n minus 1 number of edges, and so it's not connected anymore. Like this is separate to this. See that? And then likewise, like still, if I added this, if this was like this, then n is equal to m right now. I can still chop off a node and keep it connected. You see that? That's the idea. You can still chop off a node and keep it connected if there's more. And then if there's less, like here we are. Let's make an example graph with n equal 8 and m equals 6 is what I did last time. If you think about this long enough, it must have multiple components. Look, here's like 4, and then there could be like another 4 here. There's your 1, 2, 3, 4, 5, 6 nodes, or 6 edges and 8 nodes. It must be disconnected, because the second you start connecting these guys, now it's like a tree, right? Does that make sense? So give that a try and see if you can get it. So assuming you gave it a good try, let me show you my way. So proof by contradiction. So all right, if this is true, and then G is not connected, so assume that this is true, and then we'll, all right, assume that also G is connected for the sake of a contradiction. So assume m is less than n minus 1, and G is connected after all. We'll show you that the world blows up. All right, so the secret is going to have to do with the little triangle I drew before. The idea, if you have more nodes than this, you must have a cycle, right? And that's the idea here, because like if there are any more, you'd have more edges, like I was drawing here. You'd have more ways to move around in your graph, and it wouldn't be a tree, and there would be cycles, all right? It'd be over-connected. So cycles are the answer. So if G has cycles, this is the thing you need to notice. It does take a while to notice it, though. If G has cycles, you can take away edges until there are no cycles, all right? And it'll still be connected because it'll be a tree, all right? You can take away edges until there are no cycles. So do that. Let's whittle down the edges as much as possible and keep it connected, right? Because we're assuming it is connected until there are no cycles. Because there's no cycles in a tree, and we're trying to talk about trees in a second, all right? So get rid of any cycles until there are no cycles. Let's put those on the same line. No cycles. So you can do that, right? So this G that you're claiming is connected right now, if it has cycles, chop off as many edges as you need to get rid of all the cycles, all right? It'll still be connected, right? It's like if you had this many, like here's your node with a cycle at least. See how I can chop off an edge and it'll still be connected? It'll still be connected. And because you potentially just chopped off some edges, right? The new number of edges, like m prime, it is, maybe you chopped off no edges. It was less than or equal to the original m. But maybe you chopped off some. It's definitely less than or equal to right now, the number of edges in this graph without cycles. Maybe it was originally without cycles, but there's that. And then also, of course, we're assuming that m is less than n minus 1. So for sure, whatever this, how many edges we have right now, even if it's fewer, it's still less than n minus 1. Okay? But now we have a connected graph that has no cycles. Those are called trees. Yeah? That's what it means to be a tree. Yeah? So that means, so G is a tree. Now that we've chopped off any cycles, so G is a tree. You see that? And then G must have then exactly, right? We know exactly how many nodes and edges a tree must have. It must be equal to n minus 1. So G must have exactly n minus 1 edges. But we are strictly smaller than that. We know that our edges must be strictly smaller right now. See that? And that's a contradiction. It couldn't have been connected. So that, like, the world blows up. That means our assumption of this not being true is false, so it must have not been connected after all. So that proves our theorem. See that? That's a cute use of proof by contradiction. And so, yeah, I think that's every proof that I wanted to show to you today. Fun stuff. Now we know a lot more about trees, more than we knew from before. So yeah, let me show you about tree traversals. This is very similar to like the graph traversals we were talking about. There's a bunch of different kinds of depth first searches, and there's also a breadth first search, so I'll get to that in a second. But the first ones I want to talk to you about are pre-order traversal and post-order traversal. What they are a way to visit every node in the tree and process them in some way, maybe to print them out, to calculate some data, whatever you need to do. All right, so we need to decide on the order to visit those nodes, and there's several ways to do it. There are several ways in which you need to do it, and we're talking about rooted trees right now, trees with roots. So there's pre-order and post-order. Those are very common traversals through a tree, and here are their codes. Here's the pre-order code and the post-order code. They're recursive algorithms. And the way that you remember, they look the same, except for in which order, the V is like your root of your subtree right now. These algorithms are the same except for the order in which you process your root. And so pre-order means go and visit your root first, and then recursively process all your children. So root first. So it's talking about the order in which you visit the root. So pre means root first, and then post means root second, or root last. Recursively visit the children first, and then process your current node. All right. So essentially, post order is DFS. It's a kind of depth first search on trees. Okay. But pre and post are talking about the order in which you visit your root after you or before you visit your children recursively. Okay. So that is that. Pre-order and post-order. So let me show that to you. So here is a tree. Let's say that its root is D. It's the D node that's the root. And we are going to calculate the pre-order and post-order traversals. And what I mean by that is we're going to figure out like which ones are visited first, the order in which these nodes are visited. All right? So we're going to do pre-order and post-order. So pre-order. Let's give the order in which these are visited. All right, so pre-order is first you do the root. You visit the root, and then you recursively visit the children. See that? Recursively visit the children. And then for post-order, it's backwards. It's recursively visit your children first in some order, then visit the root. So post-order. That's going to be recursively visit your children, then visit the root. After all that's done. All right, so let's run this code on paper. So we got D, and we're going to call post-order on, or sorry, we're doing pre-order first. Sorry, got D, and we're going to do pre-order on D. All right, so we're going to say here's our stack. We're going to call pre-order on D. And so what does that mean? So we're going to visit our root and then recursively visit our children. So we're going to visit our root first. So D gets visited first. And we're going to recursively visit all our children. So we need to call ourselves on G and B, pre-order. So we'll call pre-order on G first, and we still have to remember to do B as well. Okay, so preorder on G happens, and so it's going to visit it. It's always a subtree, so like we're at this subtree now. We passed that subtree. Visit the root, so G, and then recursively visit the children of G, so we got to preorder on C and E in some order. So let's just do it in that order. So C, pre on C, and then, all right, we're going to, what does that mean? Preorder on C. We're going to visit the root of that subtree, so it's just this subtree with just C in it. So we're going to visit the C, recursively visit any children, but there are no children to visit, so we're done visiting C. So we pop it all off, and now we're back. Let me fix all my pens and things. So now we're back here in the call to visiting G. So it's still, we visited C, so it was always root, we did the G, recursively visit the children. So we recursively visited C, we called ourselves on C, now we have to call ourselves on E. So preorder on E. All right, which involves visiting the E, recursively visiting any of its children, there are none, and so we're ready to pop E off the stack. And so now we're back down in preorder G, we're done, and that was recursively visiting all of the children of G, so we're done there. And now we're back in the preorder of D. Its job was to recursively visit all of its children and all of its children because it visited itself very first, the first thing we did. So now we'll visit this subtree. We're going to call preorder on B. So we're going to look at, all right, the root of that subtree is B. Visit it in that order, so we just saw the B node. And then we'll recursively visit any of its children, but there are none, so this will just pop back off. Then we're back in D. It did this one, it is finished. So that is the preorder traversal order in which you're going to discover the nodes and look at them. Let's do the same for post order. All right, so post order is children then root. So post, we're going to call post order on D, and the very first thing that's going to happen is it's going to go and recurse, do a post order traversal on this subtree and then this subtree before it even looks at itself. All right, so let's go and do maybe this subtree first. So we're going to do post order on the tree rooted at G. So we're going to pass G, post on G. And so, all right, what does that mean? So it's always children, then root. So it's going to recursively visit the children. So post on C. And then, all right, recursively, we're in post order on C now. We're going to recursively visit all of C's children. There are none. And then we're finally going to visit that node. So there's our C. We finally look at C. That's the first thing that we notice, actually. I hope that makes sense. This is kind of like why it's depth first. We got all the way down to C first before we did anything else. And now we're back in G. We still need to visit all of its children. We just visited the C. Now we need to recursively visit E. So we'll do post order on E. Now that's the work at the top of the stack. And again, it's going to visit its children. There are none. Visit itself. And now it's done. And now we're back in post order of G. It's visited all of its children now. It's ready to visit itself. So notice G, and then pop itself off. It's done, finally done with all of its work. And now we're back in the post order of D call. It was working on visiting these children, and now it also has to visit its children on the right there. So we're going to do post order on B, which will visit all of its children recursively. There are none, and visit itself. So there's B. Now it's done. We're back in D. It finally is done visiting all of its children, and now it can worry about visiting itself, its own node. So there's the D there, and so now it pops itself off the stack. So yeah, those are the orders in which we're going to see things for preorder and post order. D, G, C, E, and B, or C, E, G, B, D. Okay, so that is 2 valid ways to go through the tree. These are 2 different ways to get through everybody. See that? And you don't have to keep track of like what you've seen because there is only one way to get where, which is nice. You don't have to add a visited set or anything. You're just good to go, which is awesome. And yeah, that's what I want to say about those. There are some other ones. Let's do BFS, and then but first there's one called in order. If you have a binary tree, there is what's called an in order traversal, which will visit things in a normal order. So like it works mostly for like binary search trees. Like if this was a binary search tree, right? 42, then 27 is got to be over here because it's smaller. 58, and then I can put like, I don't know, 35 here. The in order traversal on this, like you can imagine, it's going to in order go this way, in order go this way. Sorry. It's always left, root, right. So it's going to be left, root, right, the order in which it visits things, and it's going to output things in order. That's why you call it in order traversal. So it'll go and visit the 27 node first, then the 35, then the 42, then the 58, which is funny and cool, I guess. I didn't give myself nearly enough room to write that, so let me move that over. So yeah, the in-order traversal will get you, if it's a binary search tree at least, it'll give you it back in this order. 27, 35, 42, 58. There's no real reason you'd want to do this on anything that's other than a binary search tree. But it's got to be a binary tree because there needs to be a left and a right involved. Okay? These other ones work for any nodes, any children, any order of their children. In order has to be binary tree only, though. Okay? Next we have breadth first traversal of a tree now. This is exactly the same as for graphs. All right, so let me show this to you. So just you start at the root. It's exactly the same algorithm as the graph breadth first search was. Okay, that's the idea. So while queue is not empty and is the front of the queue, like you're going to push the root, you process it, and then just go through each of its children, add it to the queue. And so you're going to visit in level order. So let me show this to you. So let's give the in order and breadth first traversals of this tree starting from the root. So the in order traversal, which is all one word for a weird reason, in order, it's always left, then root, then right. Left, root, right. And it's recursively when it's going down left, root, right, left and right. Left, root, right. So it's going to go recursively in order to the left. I'm going to do this quickly now. Left, then root, then right. So we're working on the left right now. And this one's going to go left, root, right. So 1, 2, 5. So this is done left, then root, 7, then right, which is itself going to do left, root, right. So just 9 and 14 because there is no left. So that's perfectly in order. All right, and then BFS. This is really fun. I encourage you to draw it out, like draw the queue and everything, but it's just going to visit everybody in level order. It's going to visit the 7. It's going to do it in this order. Boop, boop, boop. Just like that. So it's going to be 7, 2, 9, 1, 5, 14. And I highly, highly encourage you to draw the queue and understand why it's going to do that in that order. Assuming you add to the queue the children from left to right. You got to add the 2 before the 9 and the 1 before the 5 if you want this particular order. But this is like a logical order. You could do left. Like you're gonna push the 2 and push the 9, and then they're each gonna push their children, but they're already ahead, right? So the 2 pushes the 1 and the 5, but the 9 gets visited next because it was already on the queue. Okay, so like draw it out. I promise it's useful. But that's the idea there. And yeah, before we go, I just want to talk to you about like how would you program this? Let's do it in Racket. I've made a Racket program for this, and let me show it to you. So here's some trees. Yay! So I've got. Let's see if I can find which ones I'm doing. T2. Well, first of all, here's a tree struct. What does it mean to be a tree? A node in a tree. You have your data, and then you have a left subtree and a right subtree. Okay, so that's that. And so here I am defining 2 trees, tree 1 and tree 2. And so let me show this to you. Where's the first tree? Here is this tree right here that I'm making is this one, this exact tree right here, where D is the root. So I'm making some nodes. Here's the C node, I'm making the leaves first. C node is got C as the data, and it's null left and right children. E, again, E is the data, null left and right. G is the node, the tree node called G, with C and E on the left and the right. So like these are pointers essentially. B is the tree node with, it's just a leaf. And then D is the tree node with the D name, D label, and then G and B on the left and the right. All right? And then the whole tree, like this, I want this to result in D. D is the node for the root. So tree 1 starts at D, and it's been built up like that. Then T2, for similar reasons, I make a 7 node, and that's the root of this whole thing. That's this tree. Okay? So those are the trees. And then here are pre-order, post-order, and in-order. So let's go and look at those. Here's pre-order. All it is, pre-order on some subtree you're looking at right now. So it's rooted at some tree. And so I'm going to look at the tree and figure out is this an empty tree or is it some actual tree? Because like that's what you have to worry about right now. You don't want to dereference null or anything. So the empty list is actually the empty tree for me right now, because that's what null means in Racket. It means just like empty list. Racket is all about lists. So like if the tree is empty, there's nothing to do. Do nothing at all. Just print nothing. Otherwise, if we have a real tree object here, I'm doing what's called pattern matching. That's what Racket's doing right now. So if I have an actual tree node right here, which does have a left and a right, it's valid and has some data in it, what do I want to do for that actual thing? So now I have something to do. I can process the node, first of all, so let's print it. That'll be our version of processing the node. So print the data. That's what it means to process our node, let's say. And then we're going to recursively pre-order our children, and we just have left and right. So we'll pre-order the left, and we'll pre-order the right in that order. Okay, that's pre-order. Post-order are exactly the same. Do nothing with the empty tree, and then if you have an actual tree node, do left, right, then root. Process your children before yourself, recursively. And then in order is exactly what we did. It has to be binary tree. In order is empty tree, do nothing as usual. But if you have an actual tree node, it's not null, then, all right, recursively left, visit the root, right, recursively right. So left, root, right. And so that's the in order traversal. And here I am going through these trees and doing their traversals. So Racket, trees.racket. So here are all those traversals. So it is exactly what you would expect. You got the GCEB for the pre-order, CEGBD for the post-order, and then in order as you would expect for that other tree. It's doing exactly the numbers in order. Okay, so highly encourage you to try to translate this to Racket, or not from Racket. Highly encourage you to translate this from Racket to C++. But yeah, that's, I think, as far as I want to go today. You know a little bit more about trees now. And so that's where I want to stop, and we'll come back and we'll continue the tree slides next time.